And now we're moving on to molecular and ionic compounds, section 2.6. Here we're going to define ionic and molecular or covalent compounds, predict the type of compound formed from elements based on their location within the periodic table, and determine formulas for simple ionic compounds. So, in ordinary chemical reactions, the nucleus of each atom, and that's also what gives our element its identity, does not change. So the protons and the neutrons, we don't touch them. It's electrons that are participating in chemical reactions. They're either gained, lost, or shared between atoms. And like we saw in last section, when we gain or lose electrons, the atom becomes an ion. So here's an example of a sodium atom versus a sodium cation. Okay, so the neutral atom, same number of protons and electrons, and then you can see when it loses an electron, it actually gets a little bit smaller. And then here we have 11 protons, 10 electrons, so that means we have a charge of +1, so this is the sodium plus ion. So the periodic table can be a guide for predicting the ionic charge of the main group elements. So the main group metals lose enough electrons to have the same number of electrons as an atom of the noble gas that comes before it. So they go backwards, if you will. So in group 1, they lose 1 electron. They go 1 step back on the periodic table to the closest noble gas. Group 2, they lose 2 electrons. So group 1 then has a charge of +1. Group 2 has a charge of +2. And this is where one of the first reasons why I like the A/B numberings of the groups, because this is group 1A has a charge of +1 and group 2A has a charge of +2. I know this is still groups 1 and 2, but nonetheless. Now, nonmetals like to gain electrons to give them the same number of electrons as an atom of the closest noble gas that's higher in atomic number. So they go forward. So group 17, for instance, will take 1 electron to go 1 space over to the nearest noble gas, to have a -1 charge, and then group 16 likes to gain 2 electrons, and so on and so forth. So a couple examples. Calcium, which is in group 2. Calcium atom has 20 protons and 20 electrons. So it likes to lose 2 electrons. It's a metal. So because of that, now it has 20 protons, doesn't change, but the electrons change, goes from 20 to 18, which means it has its Ca2+, and now has the same number of electrons as argon, 18 electrons. Bromine, which is in group 17, the neutral bromine has 35 protons, 35 electrons. It wants to gain 1 electron to become Br-, and this is now the same number of electrons as krypton, 36. But it has 1 extra electron than protons, hence the -1 charge. So, some ways to predict the ionic charge, going from far left to far right of the periodic table. The positive charges of cations are equal to their group number. Group 1 is +1, group 2 is +2. Now, group 3A, okay, which is not group 3, okay, that's group 13, is +3. And the only one from there that does that is aluminum. Okay, everything else in group 13 is different. It's weird. Also, you should note that this positive charge of cation is equal to the group number. Not always true, especially in the transition metals. So this is focusing on the main group elements. Okay. We're not talking about the transition metals here. Now, on the far right of the periodic table, the negative charges are equal to the number of groups moved left from the noble gas. Okay, so group 17 is 1 to the left of group 18, so it's a -1 charge. That's basically the same using the A method, so group 7A is 1 to the left of 8A, -1, 6, 5, 4, and so on. Like I said, this is not reliable for transition metals. For instance, copper forms +1 and +2 ions. Iron forms +2 and +3 ions. We're going to talk more about those soon-ish. By soon-ish, I mean I think to this chapter. So you can see kind of the pattern for the charges here. And then here's our split of metals versus non-metals. So you can see carbon here, group 14, it needs to go 1, 2, 3, 4. So it's -4 to be the same as a noble gas. Calcium, okay, if calcium wanted to be the same as krypton, it would have to gain a lot of electrons. It's a lot easier for it to give up 2 electrons to go back 1 and to argon there. 2 spots. That's just 2 little spots. I know it seems like a lot since we're jumping to the other side, but still. 2 spots +2. So far, these ions that we've talked about are called monatomic ions. There's only one atom in this ion. But there are such things as polyatomic ions, which are molecules that have an electrical charge as a group of bonded atoms. So I like to say you treat them as an honorary either metal or non-metal, depending on their charges. If it's a positive charge, it's an honorary metal, even if it's all non-metals bonded. If it's a negative charge, it's an honorary non-metal. It is made of non-metals, but you don't break them apart. And then one particular group of polyatomic ions, we have the oxyanions. And these are polyatomic ions that have oxygen. So here's a table. This is not at all the polyatomic ions in the world. There's a ton more, but these are just some of the common ones. Most polyatomic ions are negatively charged. There are some positively charged ones, for instance, NH4 ammonium and H3O plus hydronium. So these guys could act as honorary metals. But all the others mostly are negatively charged, meaning consider this entire thing as one entity, as an honorary non-metal. We do have systems for naming them. So when you have a non-metal that forms 2 different oxyanions, that means with oxygen, right? The ATE suffix is used for the ion that has the larger number of oxygens. ITE is used when you have the smaller number of oxygens. I don't expect you guys to just be able to look and guess right away, because honestly, there's no good way of naming these different ions. It's a pain in the butt. It's basically your best way is to memorize them, the formulas, and the names of the ion. And I apologize if you can hear that screaming and that crying in the background. My foster kitten wants his bottle. Okay, so when a non-metal forms more than 2 oxyanions, there's also prefixes. When you have more than just 2, so if the anion that has the largest number of oxygen, we add PER, per, to the front of it. The smallest number gets hypo for the least amount of oxygens. But yeah, it's a pretty crappy system, honestly. Like I said, you're better off just kind of memorizing them, the formulas and their names. So there are different types of bonds. When electrons are transferred, we form ions, and this makes an ionic bond. And now these are electrostatic forces of attraction. So you have a positive ion and a negative ion, and they're attracted to each other electrostatically. Electrons can also be shared to make a covalent bond. Okay, this is how we form an actual molecule. So we classify our compounds as ionic or molecular depending on the type of bonds. So ionic bonds are metals plus non-metals, because you have a positive charge and a negative charge. And covalent bonds are non-metal plus non-metal. We don't have transferring of charges or anything. We're just sharing electrons. So metals like to give away their electrons to form cations. Non-metals like to take electrons to make anions. when they react, when a metal reacts with a nonmetal, generally what happens is electrons are transferred from the metal to the nonmetal. And then we make an ionic bond because you have a positive charge and a negative charge coming together. And this makes an ionic compound. Some examples: sodium and chlorine. One sodium atom, in group 1, it gives up one electron to make Na+. And chlorine likes to take electrons. It takes one electron to make Cl-. So this makes NaCl. Because we have one positive charge, one negative charge. These come together to form NaCl. Calcium and chlorine can also form a compound. Calcium likes to give up 2 electrons, so Ca2+. And we can take 2 chlorine atoms, and each one of them can take one of those electrons from the calcium. So one electron goes to one chlorine, and the other goes to the other chlorine. So now that gives us one calcium with 2 Cl's. So we have calcium chloride, CaCl2. We're going to talk more about these compounds, how to get their formulas and stuff later. So just some properties of ionic compounds. They tend to be solids with high melting and boiling points, and they're non-conductive in their solid form. Okay, so they don't really conduct electricity. I can't just stick a light bulb that has like a positive and negative end. If I just stick it in some solid sodium chloride, nothing's going to happen. But if I melt it, now electrons are able to move around. When you have a liquid, you've got movement. So then it can conduct and the light bulb turns on. And there's sodium. Here's a better picture instead of my beautiful drawings. Sodium chloride does not conduct when it's solid, but when we melt it with lots of fire, then it conducts. So let's talk about ionic compound formulas. So an ionic compound is electrically neutral overall, meaning you have the same number of positive and negative charges overall. Okay, another thing to know with ionic compounds, their formulas are actually not molecular formulas. You don't just have one molecule of NaCl, okay, of sodium chloride. It's actually these cubic crystalline structures of positive and negative charges, kind of just in a crystalline structure. I know I'm a terrible artist, but you get the gist. So let's talk about forming some compounds. We have, let's say we have aluminum and oxygen, and I want to know the formula for it. Aluminum, okay, it forms Al3+. Okay, it's in that group 3A. It's the one that's a little different. But if you use the A system of numbering, here's my beautiful periodic table. Okay, aluminum is here. So it goes 1, 2, 3 spaces to the noble gas. So it's 3+. Okay. And oxygen is here. Oxygen, 1, 2, goes over 2 spaces to form a -2. Okay, so oxygen takes electrons, aluminum gives up electrons. So to figure out the ratio of the charges, we need to have it so that it's charge neutral. If I do 1 aluminum and 1 oxygen, it doesn't work. I have too much positive charge. So we have to figure out a way to make it so that they have the same amount of positive and negative charge. So we're going to think about things like common denominators. Between 3 and 2 would be 6. So if I have 2 aluminums, that gives me +6. And I have to multiply 2 times 3 to get -6. There we go. Those are going to cancel each other out. That means I need 2 aluminum. And we do that as a subscript. We don't put it in front. The subscript in a formula says how many are in this particular configuration. And then I need 3 oxygens to give us -6. Now there are some little tricks. I'm going to show you guys the crisscross trick, but I do have some cautionary tales for it that I will also talk about. So if you know your charges of your ions, which you should be able to figure out when you're told what atoms to work with, or you're told a name. We know I have Al3+, and I have O2-. I can change my pen color here. That's not gonna let me. Okay. It's called the crisscross method. You take the positive charge, you draw a little arrow, and now that becomes the subscript for oxygen, and the non-metal charge becomes the subscript for your metal. Al2O3. Boom. Now, cautionary tale here. Let's say we have something like I want to do calcium and oxygen. So calcium is 2+, oxygen is 2-. If we do crisscross, it looks like it's Ca2O2. But ionic formulas are more or less empirical formulas. So we want the lowest ratio. It's not Ca2O2. We need to go lowest ratio. We divide both by 2. It's CaO. So you have to make sure, because sometimes you have it where, okay, I have a -2 and a +2. Those cancel out. It's just 1-to-1. It's not 1-to-2. But let's say I want to do sodium and oxygen, Na+, O2-. Boom, boom. So this is Na2O. So it can make life easier. You can also use it the opposite way to figure out the charge of the ions in a compound. So, let's say Na2O. We can do reverse crisscross. This 2 goes here, this 1 goes here, and that Na+ and O2-. So again, cautionary tale. If I give you CaO, if you were to do reverse crisscross, it would look like it's Ca+ and O and O-. But we know that's not right because we know oxygen is 2- and calcium is 2+. So you have to make sure that you check your work. Aluminum oxide is actually what makes up most things like sapphire, but it's iron and titanium mixed in with it that gives it that beautiful, beautiful color. It's my birthstone, yay! Okay, so some ionic compounds have polyatomic ions as the cation, the anion, or both. So we treat polyatomic ions as a full unit, as a discrete unit. We don't pull them apart. So for instance, calcium and phosphate, they can combine. Calcium has a charge of 2+, and phosphate, the whole thing, has a charge of 3-. One thing I've always done is I'd like to draw parentheses around the ion just so I always remember, okay, this whole thing is this 3- charge. So if I wanted to make a compound with it, you can still do reverse crisscross. Or crisscross, sorry. I need 3 calcium, and I need 2 of this entire PO4. So this 2, so you have to put phosphate in parentheses. You put your polyatomic in parentheses, and then you put a subscript on the outside to say there's 2 of this entire thing. There's 2 PO4s. So those are ionic compounds, and now we have molecular compounds. And these come about when atoms share electrons. And these guys are actually discrete neutral molecules, and they're formed by nonmetals. A lot of times they could be gases, low boiling point liquids, and low melting point solids. They can be pretty much anything.